So we're going to continue on with our discussion of Java structured concurrency by focusing in on the structured task scope class. And you'll see that there's a couple of subclasses that are really the workhorse features of this class that you program with, called ShutdownOnFailure and ShutdownOnSuccess. And we're going to take a look at two variants. One variant is the Java 19 and 20 variant. That's what you're using for your programming assignment. And the other is the Java 21 variant, which came out recently. Changes things just a tad. You don't really have to know this for using the programming assignment, for doing the programming assignment. However, it's important to know where things are going because what was in 19 and 20 has been overtaken by events in 21. Luckily, it's not that much different. So what is Java StructuredTaskScope? As we've talked a bit about before, it's the basic foundation for Java structured concurrency. And as we've also talked about before, it's used to split a task into several subtasks that can run concurrently within a syntactic block. Remember, the whole point of structured concurrency is to get more control over the way in which tasks are created and they run, and they all have to sort of exit the scope at the same time, or when the scope is left, there's nothing left running, in accordance with the principles of structured programming, which we've also talked about a bit. That's the classic stuff from the 1970s about if statements and while loops and functions and so on. There's a couple of nested subclasses in Java StructuredTaskScope, which are really what actually do the work, and that's what you program to. It's a very curious design, in fact. When we take a closer look at this, you'll see how StructuredTaskScope is this sort of class that's the top class, the parent class, if you will, and it's got two nested classes that actually extend StructuredTaskScope. So it's a very curious way of designing the code. The first class we're going to look at is called ShutdownOnFailure, which has got kind of a funny name. But basically what it does, it will essentially capture the exception of the first subtask to complete abnormally, as it says here. And that will then go ahead and essentially shut everything down and get an exception to be thrown. If there is no failure, then all the various operations run, and there will be results from that. And what you get here is something that's commonly known as the invoke-all model. And we'll talk a bit more about invoke-all here in just a second. So invoke-all is a concept that appears in other parts of Java. For example, in the Java executor framework, which we're not really going to focus on in this class, there's this concept of invoke-all. In that case, you give it essentially a collection of callable tasks, and they all get run, and then all the results come back in the form of a list of futures to the results. So I like visuals, so we've got sort of a clone army. We're going to invoke all, and essentially the same operations can be run on all the things that are doing the computations. The second class that comes out of the box is called ShutdownOnSuccess. And this captures the result of the first subtask to complete successfully, and then, as we'll see, it cancels everything else. So this is what's used to implement something called invoke-any. For those of you who've ever watched the game show Jeopardy, that's basically an invoke-any model where a question is asked, the respondents, the participants, contestants will hit the buzzer, and whoever hits it first and gets the right answer wins the round. So no matter whether the other people knew the answer or not, doesn't matter. It's whoever hits the buzzer first. So that's called invoke-any. All right, so let's talk about how you program with ShutdownOnFailure. Now, as we've seen before in our other examples, the try with resources feature is commonly used here. You don't have to use it. You would be crazy not to use it because it's super easy to use, and it solves some otherwise rather tedious and error-prone problems. But when you do try with resources, you initialize some variable, in this case we just call it scope, of type var, which means figure out the type from whatever this is initialized with. And that means that scope is only visible within the context of the open curly brace and close curly brace. It's not visible beyond that. And the second piece about try with resources is when we go out of scope, in other words, when the closed curly brace is reached at the runtime level, then this object will have its close method called automatically, and what that'll do is clean everything up. So you can kind of think it as sort of like a destructor in C++ or in C#. Now, this particular example here uses the Java 21 version of ShutdownOnFailure. And the Java 21 version uses the supplier interface as the type returned from the fork method. The Java 19 and 20 versions, which is what you're using for your assignment, return a future instead of supplier. But otherwise, they're very, very similar. And so that's why I'm kind of showing you the Java 21 version, just because it's the latest and greatest. You'll have to translate that just a tad for assignment number 1B, but it's a really easy switch. So what happens here is we go ahead and fork a couple of Lambda expressions, and these Lambda expressions will both run in parallel. So this is the invoke-all model. So both of these calls will be run in parallel. The find user call, as we've talked about before, will go out and get some information about a user, maybe some access credentials or whatnot, some profile information about them. And fetch order will go ahead and fulfill an order or get an order result. We don't really care the details of what these things do. We just want two things to run at the same time. What happens when fork is called is a new virtual thread is created, because that's the way things work with StructuredTaskScope. And as you can see, that returns a supplier to the return value. So in the case of the user, it comes back as a string. In the case of the order, it comes back with some order fulfillment number, like an integer of some kind. There's a join method here that's used as a barrier synchronizer. Remember, a barrier synchronizer is just the thing that waits for a bunch of other concurrently running operations to complete before it can return. And this waits for all the tasks to finish, or if anybody throws an exception, then join will return. And this call here, throw if failed, will then do nothing if there was no exceptions. But if there was an exception, it will throw the exception that failed. Now, we oftentimes will concatenate these things together. You will often see scope.join.throw if failed. I didn't do it that way because I wanted to talk about each one at a time, but that's something you'll see a lot in my code. The final thing we do here is we take the results that came back from these concurrently running subtasks, find user and fetch order, and we get the result. Supplier is a Java functional type. It's been in Java since Java 8. And what it does is it returns the result that came back. In the version that's for your assignment, this will be a future, and you'll have to call the result now method as opposed to get. That's the slight little syntactic tweak. Question?
Is it possible to translate the exception that gets thrown, or is it kind of whatever you get, you then throw again?
Great question. So let's go back. So the question is, right here, this is, if let's say this throws the, I don't know, network unreachable exception or something like that. So what you can do is this will throw that exception. However, if you don't want that to be the exception, you would put a catch clause here after the close curly brace in the try with the resources block. You could catch the exception and then rethrow it as whatever exception you want it to be. So that would be the way to do it. Yeah?
So what if we don't add a throw if we fail?
What if we did? Yeah, great question. So the next question is, what happens if we fail to call throw if failed? Then something has gone wrong, and when we get to this point and we try to get these results, you'll probably get nonsensical values. So well, it depends on what the exception was. It could very well throw a null pointer exception or something. If these variables rather have not been initialized, then crazy things will happen. So I guess the best way to explain that is, if you fail to call throw if failed, then all bets are off as far as what's going to happen at this point. Now, I think the point you raised, though, is a very important point, which is this particular way of doing things requires the user to remember to do something in order to handle failures properly. Now, again, if you don't do anything, failures will still be handled. They just probably won't be handled properly as you design. So that's a good point. This requires users to sort of know what it is they're doing, which is not the end of the world, but it is a potential issue. And this is also a good example of where library-based design is often a little more tricky than things that are baked into a programming language where they could actually always check for stuff. But that's the price we pay for the flexibility that comes from using libraries. OK, so you want answers, you get answers. Whether you get the truth or not depends on whether there was an exception. But the point is that we use the get method to get the results. And as we kind of talked about in the other class last time, this behavior is very much like a sequential program where you'd say, find me the user, get the order, return the response. It's just that by using the fancy schmancy structured task scope shutdown on failure mechanism, now we have this world where these things run in parallel as opposed to running sequentially, which is pretty cool. Let's talk about how to program with Java ShutdownOnSuccess. So very similar. We also use the try with resources feature, just like we see here. The difference is that ShutdownOnSuccess is going to indicate the type of the result that we're expecting if things succeed, if the first thing succeeds. So you can see here, we give it a list of big fractions. So this particular example comes from an example that we've looked at in class last time. But just to reiterate what it's going to do, it's going to use the invoke-any semantic. So it'll take whichever result happens first. So we're going to quick sort a list and heap sort the list, and then we're going to take the results of whichever one happened to have finished first and ignore the other results. So the way this is going to work is we're going to fork off 2 tasks to lambda expressions, which will heap sort and quick sort. If you've taken the algorithms class at Vanderbilt or wherever you took it, you probably are aware that people who are algorithm theorists sweat a lot of time, which is faster, which is better, heap sort, quick sort, worst case execution time, average case execution time. That used to be an important thing. You would analyze this for asymptotic time complexity and all the different use cases and think about what the adversary was going to do to mess you up. Nowadays, with the proliferation of multiple cores, we don't care which is faster under what circumstances. We just run them both at the same time, and whichever one finishes first, we take the results. So 50 years of theory is now rendered obsolete. I'm only kidding. Theory is still important. But you get the point. We don't have to worry about these details because it's handled for us. Yes? Great question. So let me see if I can rephrase your question. Tell me if I get it right. So I think the point here is we're getting a win in time by trading off extra space, because now we have to allocate the resources to do both these things, and we're also using up 2 cores, not 1. That's absolutely right. Most people, given the proliferation of cores and the proliferation of memory, probably think that's an okay trade-off. It's usually better to make things run faster as long as you've got the resources. So as long as you've got enough memory, as long as you've got enough cores, why not, right? And in a way, that's really taking advantage of Moore's law. If you're familiar with Moore's law Moore's law is often misconstrued. People thought for the longest time that Moore's law meant every 18 to 24 months, computers would get faster, like doubly fast every 18 to 24 months. That's never what Moore's law meant. Moore's law meant every 18 to 24 months, the number of transistors available would double. And for a long time, it would also get faster, but we sort of reached a limit where it's hard to get it to go faster without encasing it in like a cryogenic chamber. So what happens instead is we have lots more transistors. What we do with those transistors is we make lots of cores. So now the use of parallel programming is very important because we're able to speed things up. And that's kind of the point here. But yeah, that's a good point. Definitely a trade-off. Nothing comes for free, but because we've got these cores anyway, why not take advantage of them? That's another example of embarrassingly parallel, where we have so much of something that we can do these somewhat brute force-like mechanisms to get better performance. So these things go off and run. And then when we do the join here, this is waiting for the first result to complete. And when we take a look at the source code, probably on Monday, next class, I'll show you exactly what it does. It's really cool to see how it works under the hood. So when join occurs, then whichever finished first is the one that we're going to take, and that's the result that comes back. And that result is a list of big fractions, as you can see up here. And that's what we're going to return from this scope. So kind of an interesting example, if you go and look at the EX3 case study, it shows both shutdown on failure and shutdown on success. OK, so that's the end of this particular discussion, which took a little longer, but it was worth it. Yes?